Welcome to physics. So far we've been dealing a lot with force diagrams, and they're not easy to deal with. The first time you learn about these force diagrams and have to make force equations with all the little angles and everything, it's a difficult thing to do. I remember going through it when I was in high school, and it was not easy. It was very, very hard for me to get a grasp on this stuff. But the good part about all this is that everything you've seen so far is not going to get any worse. You've seen just about all there is to see with force diagrams. And so what we're going to do today and going forward is work to make you more comfortable with this stuff. And that's the purpose of today. I'm going to go through 5 examples, and hopefully you can hang on to your seats, enjoy the ride, take notes, and let's see if we can handle this. Now, for most of these problems that we're going to be going through today, you're going to be wanting to solve for several different things. And it's very tempting, like if it says solve for normal force or solve for force of friction, to go to your formula sheet, try and find those equations, and then use them to solve the question. That is not the course that we take in this chapter. Every single question that you have in this chapter with force diagrams and force equations, the way that you solve it is by creating a force diagram, making a force equation, and then solving for what it's asking for. So resist the urge to just look on your formula sheet to try and solve these questions quickly. That's not how it works. We have to use force equations and force diagrams. So let's get started here. We've got an object. It is sitting on a table. It is 10 kilograms. There is a 10 Newton force pushing down on it. And for this question, I want to solve for normal force. And that's what I'm going to be doing. So if I want to start this, again, I do not look on my equation sheet or my equation shirt to try and solve this. I want to start with a force diagram. And I've got gravity going down, as always. And I've got normal force going up. Now, normal force is going to be bigger than gravity in this case, because as you're pushing down on the table has to exert more effort and force to keep the object from falling through. So it's got a bigger normal force than gravity here. Furthermore, we do have that force pushing down, and every time we have a pushing force, we call it an applied force. So we've also got this applied force heading downward. So that's what our force diagram would look like here. Feel free to make your dots a little bit bigger so these arrows aren't so crowded. But once we're here, now we can use our force equation and try and figure out where to go. So in terms of a force equation, again, it's just all the forces go in one direction minus all the forces go in the opposite direction. And in this case, normal force is the only thing going up. So my equation is going to be normal force minus force of gravity and applied force. And that's all equal to 0. So normal force up, and from normal force you're subtracting the combination of gravity and applied force. So, if I want to figure out my normal force, I just isolate it in this equation. And I do that by pulling these two guys to the other side and then solving. So then normal force is equal to force of gravity plus applied force. And then I should get my answer. So force of gravity is just mass times 9.8. So 10 kilograms times 9.8 is going to be 98. Meanwhile, I've got my applied force. That's 10 newtons. So, to get my normal force, I go 98 newtons plus 10 newtons, and that gives me a final answer of 108 newtons, and that would be my normal force in this case. Alrighty. Take a minute just to digest that. And from there, we are going to go on to our next problem. This one's going to be a bit more complicated, and it's going to be a different color. Time for green. Now we've got an object on a table. And it's going to be that same 10 kilogram object. And we've got a force that's pulling it at an angle, at a 40-degree angle. That force is the same 10 Newton force that we were exerting on the other object, going straight down. Now it's going up at this 40-degree angle. So what I'd like to solve for in this case, once again, is normal force. What is that going to be equal to? So I'm going to go ahead, create a force diagram. I'll make a force equation, and hopefully that brings me to the solution. So gravity is always going down. Once again, even if you're not confident drawing force diagrams, start with gravity, because that means that you haven't done anything wrong yet. Next, we've got that tension force, because it's being pulled. That's going up at a 40-degree angle. Now, in this case, we'll say that the surface is frictionless, so it would be accelerating to the right in this case if there's no friction and you're pulling on it like that. So the only other force here is going to be a normal force. So then the question is that normal force bigger or smaller than gravity in this case? And if you kind of go through the reasoning that we've done in the past, you realize that because we are pulling up on this object, the table has to do less work, exert less force, less effort to keep it from falling through. And so our normal force there is smaller than gravity. Oh, I mislabeled this. This is tension force. So, if I want to figure out normal force here, what I need to do is I need to do a force equation in the direction of the normal force. So normal force is up-down. So I'm only going to be looking at my up-down forces here. If I was looking for something horizontally, I'd be looking at the horizontal forces. But I'm not. So I need to look vertically. So vertically, I've got a couple things going on here. I've got normal force, I've got gravity, and I've sorta got this tension force here. It's acting partially to the right and partially straight up. So what I need to do, if I'm going to go anywhere with this, is I need to break up the tension force into its x and y components. I'd call this tension in the x direction. I'd call this tension in the y direction. Now, it doesn't really matter to me what's going on with tension in the x direction here, because I'm not looking for a horizontal force. We're not asked for any horizontal information. So I don't need to worry about calculating that. But I will eventually need to find tension in the y direction because it plays into the other vertical forces here. So next step is making our force equation. So when I go ahead and do that, I'm looking up and I'm looking down. So going up, I've got normal force. And going up, I've got tension in the y direction. And because they're going in the same direction, I'm adding them together. From these two upward forces, I am subtracting gravity because it's going down. And so that all together equals 0. And if I want to solve for normal force, I isolate it in the equation. If I get normal force by itself, I put force of gravity on the other side, making force of gravity positive. I put tension in the y direction on the other side, making that negative. And so now, in order to get normal force, I just have to do a little bit of subtraction here. So force of gravity is something that's easy to find. Force of gravity is mass times 9.8. Well, 10 times 9.8 is still 98. So that's what force of gravity is. Now, if I want to solve for my tension in the y direction, that's a little bit more complicated. You can see it in red here. It's the opposite side of this triangle. And I know on this triangle, from the information I'm given, that the tension force is 10 newtons. So I know the hypotenuse, I know the angle, I want to solve for the opposite side. And if you're solving for the opposite side, you should know that that means you're going to be using a you're going to be using a sine equation, because sine of an angle is equal to opposite over hypotenuse. So in order to solve for my opposite side here, I'm going to go sine of 40 degrees equals opposite, which is FTY, over hypotenuse, which is 10. So if I want to solve for FTY, I multiply both sides by 10, and then I can get my answer pretty quickly. You can see I put units in here, 10N, 10 newtons. I don't really care if you have newtons in the actual equation with the numbers. What I really care about is that your final answer has the proper units on it. Might be a good habit to throw the letters in with the numbers right away, but whatever you feel like. So 10 newtons times the sine of 40. I got 6.43. So that is my tension in the y direction. Ergo, I've got both numbers to figure out my normal force now. So 98 minus 6.43 is going to be 91.6 newtons. So my normal force then, 91.6 newtons. Hurrah! Alright, so there's that one. Now, take a moment, if you haven't already, take all this in, have some popcorn. The next question we're going to be doing is very similar to the one that we just completed. We're still going to be looking for normal force. Normal force equals question mark. But instead of us pulling up at an angle, we're going to be pushing down at that angle. So there you go. Same degree and everything. So we're just going to try and solve this one now. So, force diagram comes first. We've got our force of gravity. It is still the same, because it's always just mass times 9.8, unchanging, unless you go to the moon or another planet. We've also got normal force going up in this case. Normal force is much larger here than force of gravity, and the reason for that is because we are now pushing down on this object. And if we're pushing down on the object, the table has to exert more effort to keep it from falling through. And that's what normal force is a representation of. So, normal force is bigger. Now, we've got this applied force coming down at this angle. And so, as I mentioned when we first were going through this, it's kind of like drawing a line that goes into your dot. And then what you need to do is continue that through. I'll do it again here. You're probably sick of me doing it the long way, but whatever. Here we go. So, if I've got this 10 Newton force, and it's going into my object, you might think of it like this. You've got your 40-degree angle here. But again, we can't have arrows going into our dot. They have to be coming out of our dot. And so what we do then is we continue this arrow all the way through, and this represents our applied force, because it's a pushing force. And because of math, this 40-degree angle is the same angle as this one here. Once you do that, you can erase everything on the right side. So that's our properly done force equation. Again, we're assuming that there is no friction here. And, all right, so now we want to solve for normal force. And just like the last one, we don't care about what's going on horizontally, because we're not looking for any horizontal information. We're looking for a vertical piece of information, the normal force. So if I want to solve for that, I need to make a force equation. But before I do that, I need to make sure that when you look at this applied force, it's acting both to the left and it's acting down. And you need to break that up into its horizontal and vertical components if you're going to go anywhere with this. So, we'll do that the same way we did in the last problem. Applied force is acting both to the right and down. Down is applied force in the y direction. Across is applied force in the x direction. And what we're really looking at for this then is the vertical information. So let's see what's going on vertically. We've got normal force going up. So that means in our force equation, we've got normal force starting. It's the only force going up. Going down, we've got two forces, applied force in the y direction and force of gravity. So from normal force, we're going to subtract both those values because they're both going down. And of course, that all equals 0. So now we play the same game that we did in the last version of this problem. If I want to solve for normal force, I isolate it in my equation. And that's what you get. When you chuck this entire summation over to the other side, it all becomes positive. So the negative disappears for that reason. So if I want to solve for these things then, force of gravity, nice and easy to get here. It's just mass times 9.8, 10 times 98. 10 times 9.8 is 98 still, just like in the last one. If I want to solve for my applied force in the y direction, it is the opposite side of my 40-degree angle. And so once again, for the opposite side of a triangle, you use sine to figure that out. So you do the exact same work you did in the last one, and you're going to get the exact same answer, which was 10 newtons times the sine of 40 degrees. And when you do that math, you're going to get the same answer as before, too, 6.43 newtons. That's the applied force in the y direction. And so now you've got enough information to solve for your normal force. You add 98 newtons to 6.43 newtons, and you get your final answer of, looks like about 104. Yep. 104 newtons would be your final answer for normal force then. And again, when I do my rounding, I go to 3 digits. That's why there's not a bunch of decimals after that number. So 104 newtons is our normal force. Again, for this part here, feel free to check out the last problem we just did. It's the exact same math to get this sine equation. Okay, well that was fun. We've got 2 more to go. The next one is, once again, going to be our same 10 kilogram mass. But now it's going to be on an angle. I know you're looking forward to that. So, here we go. I'm going to make the incline different from the last one we did in class. We'll make the incline going this way. $10 kilograms there. We'll use that same 40-degree angle. And we're going to say in this case that the object is at rest. And obviously then there's going to be a lot of friction there that's holding it in place. And not just any friction. This is static friction. So let's say I want to solve for my force of static friction. In addition, not to be left out, we also want to figure out the normal force in this case. So, if we're going to do that, we need to start with a force diagram, create a force equation, and hopefully that leads us to the correct solution. So let's see what we can do here. 10 kilograms is the mass, and it's on this incline. So let's start with our force diagram, and we got to be very careful when we make it because we're on an angle now. So let's do this. Once again, force of gravity comes first here. The reason for that is because it's always there. Always want to start with force of gravity. Next, we've got a normal force. That normal force always is going to act perpendicular to your surface. So it's on this incline. Normal force perpendicular to the surface is going to be going this way. Perpendicular, 90-degree angle. It's a bit much. There's our normal force right there. Next up, the block is not moving, so there must be some friction here. And that friction is going to run parallel to the surface. And because the object isn't moving, it is static friction, as I mentioned before. So in the same way that normal force always runs perpendicular to the surface, friction always runs parallel to it, in line with the surface. So, there we go. Now, this causes an issue, because we have to, if we're going to go anywhere with this, we need a force equation in the x and y direction. And, you know, in the past, whenever we had a force that was not exactly in line with it, what we would do is we'd do sine and cosine, we'd get that number, and we'd be on our merry way. But this is a little bit different, because now we've got 2 forces that are not acting in the x and y direction. Normal force and friction, and that simply will not do. So what we do to believe it or not, make our lives easier, is we take our x and y axes that are usually straight up and down, left and right, and in this case, we're going to rotate them a little bit counterclockwise. Your y-axis always is going to match up with your normal force. It will always be perpendicular to the surface. Your new, I'm going to draw that a little bit better. That's a little better. Your x-axis is always going to match up with your force of friction. And so that's always going to run parallel to the surface. So our new y-axis lines up with the normal force, new x-axis lines up with the force of static friction, and now our job is actually a little bit easier, believe it or not. So the only force then that is not acting exactly in the x or y direction is gravity. So let's see if we can do something with our gravity. This gravity is acting in both the x and y direction. So if, again, like I mentioned in class last time, when you're creating the force of gravity in the y direction and the force of gravity in the x direction, I don't really care if you get your arrows the exact right length. The main thing is that you realize that when you make those triangles, this is your hypotenuse. That being said, if you want to make your force diagrams look nice and pretty, you would start from the tip of your force of gravity arrow, and you would follow it to the y-axis in such a way that it hits it at a 90-degree angle. If you do that properly, then you will have the appropriate length of your force of gravity in the y direction. You can do the same thing for the x-axis then. You want it to hit at a 90-degree angle. And that's how you draw your arrow then. Force of gravity in the x direction. I'm actually I want room for the angle, so I'm going to move this over just a bit. Force of gravity in the x direction. So we've got our force diagram complete there. The only thing that it's lacking is those angles. So if I want to get those angles in, the procedure that we follow is we draw a little horizontal dotted line, like that. And what we do, if you can imagine this, is we take this triangle, and what we want to do is see which of these two sides it's going to slide into without us twisting or turning it. And so if I take this triangle and I shift it over without twisting it or turning it, you can see that the left wedge is going to slide in right here. It's not going to slide in here. I'd have to flip it around. I'd have to twist it for that to happen. So because my wedge is on the left side here, that would slide right in to this one. So that means I've got myself a 40-degree angle right there. And as you go around, these angles must add up to 90. So if that's 40, that means this is going to be 50. And 40, 50, and you get the idea there. And this is your completed force diagram with all 4 colors. So, if we are going to continue here, what we have to do is now create a force equation, because we're looking for force of static friction and we're looking for normal force. So now we've got to deal with both of those directions. Let's go ahead and solve for normal force first, because that's what we've been doing this whole time anyway. So a normal force is a force that's acting in the y direction. So let's take a look at the forces that are acting in that line. In the y direction, we've got normal force going one way. And we've got gravity in the y direction going the opposite way. And because this object is not accelerating in this direction or through underneath the incline, this equation is equal to 0. And in this chapter, all of our equations will be equal to 0. Now, I have enough information to figure out what my normal force is. All I got to do is look at this force equation, isolate that normal force, and then solve. Normal force, then, is going to be equal to my force of gravity in the y direction, which is right here. Now, if I want to solve for this side of this 40-degree triangle, I need to know something else about the triangle. And I do, because as we've done in the last 3 examples, when we calculated force of gravity, it's just mass times 9.8. So 10 times 9.8 is 98 still. So 98 is the hypotenuse of that part of the triangle there. So if I want to figure out the adjacent side, that means I got to use cosine, because cosine of an angle is equal to adjacent over hypotenuse. So let's see where that takes us. So cosine of 40 degrees is equal to adjacent, which is FGY, over hypotenuse. And my hypotenuse is 98 newtons. So then if I want to solve for force of gravity in the y direction, I have to multiply both sides by 98. So that's what I do. And when you do that math, and your calculator is properly in degree mode, you get 75.1 newtons. So 75.1 newtons is equal to your force of gravity in the y direction, and therefore equal to your normal force. So that's what we have there. Next up, force of friction. Force of friction is acting in the x direction. And we've got 2 forces acting in the x direction. So let's see what we can do with those. In the x direction, we've got gravity acting and force of friction acting. This one's kind of an interesting point here, because usually, it's pretty easy to tell which one you should make positive. Friction is always negative. Gravity is usually negative, but in this case, we've got gravity and friction opposing each other. So which one do we make negative? In this case, we're going to make friction negative. Resistance to motion always trumps anything else. So even though gravity is usually negative, gravity is actually positive in this case because friction is opposing that motion. So in my equation then, it's going to be force of gravity in the x direction minus force of friction, force of static friction, equals 0. Therefore, if I want to solve for my force of static friction, I just chuck it onto the other side of the equation, and you can see it's equal to force of gravity in the x direction. So now this becomes another game of us calculating force of gravity in the x direction. Once we get that, then we're good to go, because that is equal to force of static friction. So, I want to mention, well, I'll go through this way, and then I'll just mention something quick. What I do is I like to solve these questions in terms of the direction that their force is pointing, directly on the axis. And so force of gravity in the x direction is right here. It is the adjacent side of this 50-degree angle, and because it's the adjacent side, I'm going to be using cosine. So cosine of 50 is equal to adjacent, which is FGX, over hypotenuse, which is still 98. So force of gravity in the x direction is equal to 98 times the cosine of 50 degrees. And when you do that math, I get 63 newtons. And that force in the x direction is equal to my force of static friction. So there you go. What I wanted to point out is there's another way to do this. You can see I've actually made two triangles here, this one and this one. If you're the type of person that just, maybe you're like, one triangle is enough for me. I don't want to deal with the second one. So you can do that. You could just use this triangle, or you could just use this one. Let's say we did the first part using this triangle, and you just want to use that for the second part as well. So if you're looking for force of gravity in the x direction, that force of gravity in the x direction is also equal to this side of this triangle. And so instead of saying cosine 50 is equal to FGX over 98, this is the opposite side of the 40-degree angle. So you'd say sine of 40 is equal to FGX over 98. So your final expression would be 98 times the sine of 40, which will give you the exact same answer. So you could do the same thing the other way too. You could use this side of this triangle to solve for FGY. Okay. One more. Stick with me for one more. If you're bored, just look at the Christmas lights. So we're going to use this same 10 kilogram mass here. But now our mass is not on a table or anything. Now it's suspended by different strings here. And we've been using 40-degree angles, so we might as well not change that story. So we've got a 40-degree angle on the top left there. And we've got two tension forces then. We'll call this tension force 1. We'll call this tension force 2. So my question then is, what are those tension forces equal to? And that's something that we can solve just by knowing the mass of the object. And again, you're not going to be looking on your force equation for answers to these questions. I think I said that wrong. You're not going to be looking on your force equation sheet for answers to these questions. You're going to be making a force diagram, a force equation, and then you can find your way to the answer. And this is no different. So we've got our 10 kilogram mass here. Going down is force of gravity. We've also got a force going up and to the left. That is FT1. And we've got FT2 going straight across. So if we're going to do anything with this, we need an angle. So you can see we've got this 40-degree angle there. So if you can imagine making a 40-degree angle right here, that 40-degree angle will be equal to that angle right there because of math. But if you're not quite sure about that, and you're not quite sure if the angle is going to be equal there or not, one thing you can do is just say, what's going to happen if I make this angle smaller? well, if I make this angle smaller, this angle is going to get smaller too. So chances are they're the same angle. So there's our force diagram. And you can see if we're going to do anything with this, we got to deal with our delinquent tension force right here. And we got to do that by making it in the X and Y direction, as we've done with these forces in the past. So tension 1 is acting both horizontally, I'll call that FT1X, and vertically, call that FT1Y. So we break up that tension force into its two components because it's not going exactly to the left. It's not going exactly up. It is doing both. And so what we have to do is divide it up into those X and Y components if we're going to hope to solve anything here, which we are. So if I want to figure out we're going to solve for tension 1 and tension 2. If I want to figure these things out, I got to look in the directions that they're pointed. So for this one, let's take a look at, let's take a look vertically first. Because vertical information is the only information that we're really given here. Gravity is the only number that we know. We don't know anything else. So it's probably best to start in the direction of gravity. So gravity, like all the other examples, is equal to mass times 9.8. So 10 times 9.8 is going to be 98 newtons. So we know gravity down is 98 newtons. So let's think of this vertically here then. Vertically, for our force equation, going up, we've got tension 1 in the y direction. Going down, we've got force of gravity. And those are the only two vertical forces acting here. So, if I want to try and solve then, what I'm going to do is I'm going to put force of gravity on the other side of this equation. And look at that. Tension 1 in the y direction is going to be equal to force of gravity, which is 98 newtons. So that means that this opposite side of the triangle is 98 newtons. That's going to help us. Because now we've got the opposite side of this triangle, and we know the angle. And if we know those two pieces of information, we can solve for the hypotenuse. And you can do that with a sine function, because sine is equal to opposite over hypotenuse, the two pieces of information that we're looking at. So, sine of 40 degrees is equal to opposite, which is 98, over hypotenuse, tension 1. So now if we want to solve for this thing in the denominator, we got to multiply both sides by it. That comes out in front. Divide both sides by sine 40, and then you have your expression. And when you do that math, and when I do that math on my favorite little calculator that I've had since 5th grade, I get 152.5. Because I round to 3 digits, I'm rounding to 152. 152 newtons is tension number 1. So tension 1 is 152. Now, all that's left is to solve for tension 2. And so that's the next step here. So we have to look horizontally if we're going to be solving for that force. So what I'm going to do is I'm going to create a horizontal force equation. So going to the right, I've got Ft2. Again, this is horizontal, so those are the only forces that are going to be in this equation. Going left, I've got tension 1 in the x direction. And there's no other horizontal forces, so that equation is going to be equal to 0. So, tension 2 is equal to tension 1 in the x direction. Yay! So, from this then, to get tension 2, all I got to do is solve for tension 1 in the x direction, which is right here. And I know tension 1 was 152. So you can see you've got several ways you could solve for this adjacent side of the triangle. What I'm going to do is use cosine because, I don't know, it seems like I'm always using cosine. It's a very trusty function. So cosine is adjacent over hypotenuse. So cosine of 40 is equal to adjacent, which is ft1x, over hypotenuse, which is 152, and therefore tension 1 in the x direction is equal to 152 times the cosine of 40 degrees. And when you do a little bit of multiplication, I got 116. So, finally, the end of the story. 116 newtons is equal to tension 1 in the x direction, which is equal to tension 2 because of our force equation there. And that is all she wrote. Take one last look. And I'll see you guys later.